Assalamualaikum and greeting to everyone. Green Gardens, a team from University Kebangsaan Malaysia, and we'll be presenting a naphtha cracking innovation for INNOSIM 2023. Green Gardens consists of three members. The first member is Yusuf Al-Mubin bin Shaharin Anwar. The next is me, Muhammad Fauzan bin Aminuddin. And the third one is Abdullah Yusri bin Abdul Karim. We are all from the Bachelor of Chemical Engineering program. This is our agenda for our presentation. We'll be starting with literature view, and the next we'll be discussing about the process flow diagram of general naphtha cracking, the concept of the simulation, the technical and market analysis of the hydrogen production with the method selected, the sustainability of the plant design, and lastly we'll be conclude in the conclusion. First and foremost, literature review. First method of hydrogen production selected method is steam methane reforming, or in short SMR. SMR is a process that uses catalysts to react natural gas or other like hydrocarbons with steam to produce a hydrogen. And why it is still relevant is due to its nature of mature technology of producing hydrogen with high energy efficiency with up to 85%. It is also produced most of the hydrogen in the world by the chemical industry. Three reactions found in the SMR process, two reactions in the SMR reactor, which is SMR and DSMR. The feed of methane will react with the steam to produce an intermediate product, carbon monoxide and hydrogen. The second reaction, direct steam methane reforming, is using the methane and steam to produce a direct carbon dioxide and hydrogen. The intermediate product later on from the SMR reaction will undergo WGS, water gas shift reaction, to produce a carbon dioxide. The unit operation involves firstly the SMR reactor, which operates at 850 degrees Celsius, the WGS reactor, which operates at 3 to 400 degrees Celsius to convert CO into CO2, and the pressure swing adsorption is used to remove CO2 from the mixture of hydrogen gases, which is up to 95%. The emission issue of the SMR process is due to the reformer contribute to up to 80% of the greenhouse gases emissions. It is proven industry sector in the US in 2020, where the GHG emission is approximately 41.3 metric tons produces. The next selected hydrogen production is water hydrolysis. Hydrolysis of water is a chemical separation of water molecules into hydrogen and oxygen elements. And why water hydrolysis is selected? Water is considered as an abundant source and a convenient source of hydrogen. It is considered as a clean energy source due to not producing greenhouse gases and other harmful pollutants. It is also developed by efficient catalysts. It is possible to power by renewable energy, which is make it as sustainable. The chemical reactions depends on the type of water hydrolysis. Firstly, the PEM, where the hydrogen reduction at anode, alkaline, and SLE, the reduction of water which occur at cathode, which is different from PEM. The unit operations typically around 50 to 200 degrees Celsius, and operating pressure at 2 to 10 bar, which required a specified electrode and electric current. The emission issue, while the water hydrolysis does not contribute to the greenhouse emission, but it does consume a lot of electricity.
Now let's move on to the process flow diagram of our study. This study focuses on steam cracking of naphtha. The process begins with the feedstock, where final analysis is done using the composition shown to ensure accuracy. The naphtha feed is preheated to optimize cracking reactions and improve efficiency. Below the preheater is an economizer which recovers waste heat from the flue gas to the transfer line exchanger, which also improves energy efficiency. The naphtha from the previous preheater is mixed with steam to reduce coke formation, and below that, coils inside the furnace are used to generate high-pressure steam by transferring heat from the flue gas or other sources to water. This is essential for diluting the naphtha and providing heat for the cracking reactions. The second naphtha steam preheater further preheats the naphtha steam mixture to reach the desired temperature before entering the radiant section. The radiant section is where the most thermal cracking occurs. Larger hydrocarbon molecules are broken down into valuable petrochemicals such as ethylene and propylene. This is the fuel burner, which is used to heat up the whole furnace, and then this is the transfer line exchanger, which is used to cool down the products to prevent overcracking. A boiler is used in this study to generate high pressure steam by burning fuel. Steam is used for dilution, temperature control, and providing heat in the cracking furnace. These stages collectively ensure efficient and controlled cracking of naphtha, leading to the production of valuable petrochemicals. So in this simulation, we shall compare the fuel used to heat up the furnace. So there's two methods: the conventional method, which is just like natural gas, and hydrogen-based cracking, which is steam, methane reforming, and electrolysis, which produces hydrocarbon. Steam methane reforming is one of the methods of producing hydrogen in this study. This diagram that we took from symmetry is the representation of the process. SMR is a widely used process that involves the reaction between methane and steam to produce hydrogen and carbon dioxide as shown in the diagram. It's important to note that SMR is an energy-intensive process requiring a significant heat input, but nonetheless, SMR is highly efficient and enables large-scale hydrogen production. It utilizes abundant natural gas resources and yields high-purity hydrogen. Now let's take a look on our electrolysis-based hydrogen production plant. Now as you can see, the input for the electrolyzer is only water. On the other hand, the product from this process is hydrogen and oxygen. In this case, hydrogen is used for the fuel of the furnace, whereas oxygen is the byproduct that can be sold to reduce operational costs. In this process too, we've opted to recover energy from the flue stack and exhaust from the furnace to heat up water to operational temperatures while reducing energy demand. While the beauty of water electrolysis lies in its ability to generate hydrogen without any carbon emissions, one major challenge of this approach is its substantial energy requirement due to the endothermic nature of the reaction. Electrolysis demands a significant amount of energy to facilitate the process, thus the need of utilization of energy recovery. From the case study explained, we've simulated the process using the 2022 version of SLB symmetry. Let's have a look on the results. As mentioned before, SMR and electrolysis has lower emissions than the conventional method. In our simulation, SMR and the electrolysis method emitted 155 and 10.1 kilotons per year. From this, we could conclude that SMR could reduce 13.8% emissions of the conventional method, while electrolysis could reduce a whopping 94.4% compared to the conventional method. In this study, energy demand is only considered for electrically and fluid-heated utility and fuel production. This consists of boiler, pumps, electrolyzer, and SMR reactor. Our simulation concluded that SMR method requires a 138% increase in energy demand, while electrolysis method requires a 477.8% increase in energy demand compared to conventional method. However, if we look at the energy demand of the steam furnace, the simulation shows an opposite result, where SMR and electrolysis method requires 35.4% less energy to undergo the same process. In our analysis of utility and power generation energy demand, we have also conducted a thorough assessment of the associated costs for the three processes. And remarkably, we have discovered that steam methane reforming method exhibits the lowest cost of operation, amounting to only 79.33 million ringgit, and this is followed by the conventional method at 112.37 million ringgit and electrolysis at 134.38 million ringgit. It is also important to note that these cost estimates do not encompass the expenses related to process design, control system, and maintenance. It is evident from our findings that hydrogen derived from steam methane reforming presents itself as the most cost-effective fuel option. Now, the product of the process mainly consists of water and products of cracked naphtha, where ethylene and propylene is the major products with composition of 16 and 11% of the total product stream.
In summary, from all the technical analysis conducted, it is found that SMR excels in all parameters required. Firstly, if we go into the emission categories, the SMR and electrolysis relatively produce lower GHG emission compared to conventional method. It is opposite for the energy category for electrolysis, where it is require a lot of energy consumption to undergo a chemical separation compared to conventional and SMR. Lastly, for the cost, conventional and SMR require lower cost compared to electrolysis. Hence, overall, SMR is preferred methods for hydrogen production.
Next, we move to market analysis. From the figure, we can see that water electrolysis had a huge potential to grow compared to steam reforming. With market currently major held by the steam reforming, with market size of 0.8 billion, it expected to grow to 1.2 billion in 2030. In the other hand, hydrogen production using water electrolysis currently have a lower market than steam with the value of 0.6 billion, but it is expected to grow up to 5.3 billion in 2030. The significant increase happened due to the demand and acceptance of the consumer. With promotion of sustainable, more greener method sure had an advantage. Other than that, technology advancements will lower production costs via more considerate water electrolysis condition. Innovation towards sustainability also increase the investment to green energy as competition among companies to fulfill cleaner production.
The United Nations adopted the Sustainable Development Goal (SDG) in 2015 as a comprehensive and inclusive initiative aimed to addressing poverty eradication, environmental preservation, and the promotion of peace and prosperity for all individuals by the year of 2030. Next, we will explore how the Sustainability Development Goal (SDG) can be efficiently advanced through the utilization of hydrogen production via steam methane reforming (SMR). The utilization of small modular reactor facilitate the generation of environmental friendly energy at a cost that is deemed reasonable, thereby aligning with the objective outlined in SDG 7. In addition to this, SMR also offers sustainable energy supply to cities and communities aligned with the principle of SDG 11. The fulfillment of the SDG 12 was also further achieved through the facilitation of hydrogen production as more environmentally friendly substitute for conventional fossil fuel. The technology in the question has also contributed to the advancement of the climate action as outlined in the Sustainability Development Goal 13. The present analysis examines the manner in which water electrolysis contribute to attainment of Sustainable Development Goal. This technology utilizes water and a water treatment facility to deliver clean water, thereby contributing to the achievement of SDG 6. Water electrolysis does not generate any emission and align with SDG 7. In addition to this, the process of water splitting to obtain hydrogen was to be found to stimulate the development of novel methods for hydrogen production. Achieving clean combustion represents a crucial stride toward addressing climate change and mitigating the effect of global warming. To conclude, we can summarize that considering the current technology landscape, steam methane reforming (SMR) emerged as a most favorable choice due to its affordability and slightly lower emission. As a stopgap measure, SMR effectively bridged a gap until a more advanced large-scale electrolysis technology became available for steam furnace cracking. Some suggestion was made such as hydrogen and water in the product stream. Some suggestion was made such as hydrogen and water in product stream can be recycled to reduce water or methane as feed. Renewable energy as electricity source for electrolyzer, steam from the furnace can be used for energy recovery and better coil technology for steam cracking furnace.